Welcome to Part 2 of Variography with Sage 2001. Recall in Part 1, we did some exploratory data analysis on a sample data set. The idea of exploratory data analysis is to learn something about the statistical properties of our data so that we can set up Sage 2001 for the calculation of sample variograms. If Sage 2001 is set up properly, we should obtain sample variograms that are realistic models of the spatial continuity of our data. However, before we get started, I'd like to do a quick review of the sample data that we explored in the video Variography with Sage 2001, Part 1. Recall that there were 89,419 blast holes in the data set. The blast hole coordinates are in columns 1, 2, and 3, followed by fire assay, bench elevation, a gold indicator, rotated X and Y coordinates, and a domain variable. Domain wasn't shown in the video Variography with Sage 2001 Part 1, so that's primarily why I am reviewing the data set here. So let's look at the level maps of the data and see how the domains are defined. These are the same level maps shown in the video Variography with Sage 2001 Part 1 with the addition of domains. The main shear zone, which contains most of the gold mineralization, forms one domain and is called the shear domain. You can recognize the shear domain by the colored blast hole grades. The other domain is the footwall domain. You can recognize it by the dark patches on all 6 levels. Remember, the gold grades within the footwall are much lower than those in the shear domain, and their spatial patterns are not as well defined as the mineralization patterns within the shear zone. All right, I think it's time to introduce Sage 2001. Sage 2001 has been around for many years, and it is virtually bug-free, but it does have some limitations, and one is a short path to your working directory. For example, if the path to your working directory is too long, your path name will overflow the buffer within Sage 2001, and the program may crash. I work around this problem by creating a folder with a short path like C/variography as illustrated here. And then I do all of my variogram calculations and modeling within this folder. Copying files in and out of this folder is a bit tedious, but it always works. All right, let's get started by clicking on the Sage 2001 icon. Sage will respond by showing you a splash screen for a few seconds and then displays the initial menu screen. All right, we want to start by importing our blast hole file into Sage. So we can do that by click on Variography, then followed by click on Calculate Sample Variograms, followed by Import File. That'll open up our folder where we contain the blast hole data. Click on au.txt, say Open that. Sage is now reading in the blast holes. As you can see up in this corner, it read 89,420 blast holes. Now in row number 1, we have our header file, and so there we recognize the blast hole coordinates X, Y, Z, fire assay gold, bench, the indicator, rotated coordinates XR, YR, and the column of rock type. Notice on row number 7 here, it's got numeric, 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 and we get down here to categorical. So categorical variables are treated differently than numerical ones, right? So Sage has recognized that rock type looks like got characters in it, so it called it a categorical variable. We have an option, though, of changing that if possible. Sometimes people have rock types as integers. So suppose indicator here, we wanted to change that to a categorical. We could just click on here, click on categorical, and now the gold indicator is a categorical variable. So we could do that with a rock type variable if our rock types were integers as well. Generally, we want rock types to be a categorical variable, no matter whether they're character or integer variables. I'm going to leave my indicator as numeric. Another option that Sage has is see on row 6, it's empty here. If we didn't have a header record here, we could create one in row 6. We could give each of these columns a name in row 6, and then we would say use row 6 for column headers. We do have a header, so we're going to use row number 1 for the column header and leave it at that. When I click the next button here, Sage is going to create its own file, which is a .sag file. It has its own particular formatting that Sage likes. Once we have a .sag file, we can then open the file rather than import it the next time we want to work with that file with Sage. So let's click Next. Sage says OK. It's going to be a Sage2001 file, a .sag. I'm going to have to give it a prefix here, which I will call AU. So we'll have a file called au.sag. Save that. So then Sage responds with a screen where it's asking us to select the different variables that we want to work with. We don't have a borehole ID, so we'll just leave that not selected. Let's look at the X, Y, and Z coordinates and attribute. So the X coordinate, Sage just says, the variable you want for that is XR. Well, that's the rotated one. We don't want that. So let's change that to the regular X coordinate. It selected Y column for the Y coordinate, the Z column for the Z coordinate. That's fine. We get down to attribute number 1 here. What we want to calculate sample variograms on is fire assay gold, so we select that. Sage reads that column of data values and says the minimum is 0.005, the maximum is 149.7 grams per ton, and you will remember that is an outlier. You remember from our exploratory data analysis in part 1 that we said everything greater than 3.87 is going to be considered to be an outlier and will eliminate all outliers from future calculations of sample variograms. So we put in a maximum here of 3.87, and that's exactly what will happen. Let's go down to select constraints. We want to constrain the selection of our sample data, let's say, to a particular rock type. So we go down to attribute number 3, open up here. We have a variable here, which remember is rock type. We click on rock type, and it opens up and says you got 2 rock types. You got the shear and the host. We want to calculate sample variograms only on the data in the shear rock type. So we click on shear and leave host unselected, and that will eliminate all the host samples and only use samples within the shear rock type. We could have several rock types there, and we could select samples from 2 or 3 different rock types and so on and so on. When we click next, then Sage will open up another menu, and this time we're expected to enter in all of the distance and tolerance parameters that Sage will use for calculating sample variograms. So let's go through these. The first one is directional increments. So it's going to go around the clock on azimuths, and it's going to increment the azimuths by, in this case, 30 degrees. We could select something else. We could select 45, 60, or 90. I'm going to leave it at 30. Then it's also going to go through a number of dip angles at the same time, and it'll increment the dip angle here by 30 degrees. And again, we could select something different, 15, 30, or 45. I'll leave it at 30. Okay, let's move over to bandwidths. By the way, if we don't know, or we have not quite sure what some of these things are, like bandwidth, we can always go to the context help menu. So if I click on F1 now, it opens up a help menu and gives me a lot of information that is pertinent to that particular screen. So here we have information on azimuths, dips, lags, tolerances, directional increments. That's what we just went through, right? Lag specification. And here's one on bandwidths. So this little diagram maybe should help explain what a bandwidth is. So let's say we have, this is our search vector here that's pairing up data, this black arrow. So let's say we have a sample at the tail of the vector and we're pairing it up with some other samples that are at the head of the vector or somewhere out here. All right, what a bandwidth does is it eliminates all samples that are outside of these planes. So if there was a sample to the left of this vertical plane, it would not get selected. If it's to the right of this vertical plane, not get selected. And then if we look at the horizontal planes, if it's above this top plane, it would not be selected. If it's below the lower plane, it would not be selected. So the sample must be in that little box that you see before it will be paired up with whatever samples at the tail of the vector. The thing to notice here is that the distances, you can select the distance, mean it's the total distance between those vertical planes or the total distance between the horizontal planes. So those are your bandwidths. Then there's other information there about customization and so on, but I'll cover that. So our horizontal bandwidth, sort of a rule of thumb here, you remember the nominal spacing of our data was 4 meters. If I set a bandwidth that's a little bit more than twice the nominal sample spacing in this case, that'll probably do quite nicely. So let's select 2 times 4 is 8, a little bit more is 10. And same for the vertical, 10 and 10. All right, let's move down to lag specifications. Here we say the unit distance. Well, in our case, remember, it's 4 meters. And the maximum number of lags, we'll leave that at 50. So the largest, longest, biggest lag that we will get will be 4 times 50, which is 200 meters, okay? Then we can move over to tolerances here. These are the angular tolerances. So, and the lag tolerance. A lot of people like half of the lag, in other words, 0.5. I generally like to slim it down a little bit, 0.4, 0.45, something like that. So I'll leave it at 0.45. If you want 0.5, that's fine with me. The angular tolerance. Well, we're incrementing the horizontal azimuths by 30 degrees. So half of that would be 15 degrees, and that would be a good angular tolerance. So I'll put in 15 here. Okay. The thing to note here then is this the last option, which is customize the azimuth, the dip angle, and the unit distance values. And we're going to check that box because we're going to customize it. The thing that you should know is that Sage uses all of these values in the spreadsheet to, these are the parameters that will control the estimation of the directional sample variograms. When we filled up these boxes up on top here, like bandwidths and azimuths and lag distances and tolerances, some of those values were populated down into this spreadsheet. We can go to this spreadsheet, however, and edit it. So for example, you remember from our exploratory data analysis that the strike of the major shear zone was roughly about 45 degrees. So if I look at the azimuths at which Sage will currently calculate directional sample variograms, I don't see a 45 degree here. It would probably be a good idea to calculate a directional sample variogram as close as possible to the strike of that shear zone. So we would like to put in 45 degrees here. And then we're going to have to go through, well, we don't have to, we could just leave it. But I'm going to go through and increment that by 30 degrees. So 45 plus 30 would give me 75. Then we're going to go to 105, 135, 165, 195. Let me see, what is this? 225. A hard time adding 30 here. Then we go to 255, to 285, to 315, to 345, Now 345 and 30 is 375, which is the same as 15, right? Okay, so we got those things set up. What about the dip? Well, remember, we thought the dip of the main shear zone was something around 50 degrees. So I would also like to calculate a directional sample variogram that is at a dip of 50 degrees. So let's put it in there, minus 50. And I could change these other things too. I don't really know. I could leave it at minus 30, but I'll take half of that at minus 25 and leave the minus 90. Okay, so now we've edited our spreadsheet, and Sage is going to use these values now for calculating the sample variograms. Note that we could also change the lag here. So often you'll get the vertical distance much different than the horizontal different. So this is a good place where you can change that. Next, let's give it a title here. Let's say this is in the shear zone and it's gold. So that would be the title of our plots that we're going to get in the sample variograms. Now we have several different estimators that we can use. We have the parallelogram. We have the traditional thing. That's the traditional variogram estimator that initially came out in the first several books of geostatistics. We have the pairwise relative estimator, which is a product of Michel David. We have the parallelogram, which I think Mohan Srivastava and myself introduced to geostatistics back a few years ago. And we have an indicator approach. So if you wanted to do an indicator variogram, you could create one here. You could say, I'm going to do an indicator, and I'm going to do it at a cutoff of whatever you want, 0.5, and it will create an indicator, and you will get your sample variograms. Well, we really don't want to do that. We're going to use the parallelogram. You can have an option to make a log transform if you wish. Now, here is something percent of samples. If you had a very large sample database, let's say you had several 100,000 blast holes, it may take you several days to calculate a sample variogram, whereas you could take a random subset of those samples and get exactly the same variogram using a random subset. So here you could set the random subset to whatever you wanted. You want 50%, 40%, 25%, and it'll go through your initial blast hole data sets and create a subset by randomly selecting them. Output file names. Report, the autofit file, the plot file. Sage has given us some initial names here, which I will keep. The au.rpt for report, PLI for the autofit file, and PLT for PLT, a plot file, which we don't really use very much. All right, then we can say finish. We're ready to go. Sage then opens up a little progress window, and it tells you what's going on here. So it says calculations are in progress. We see this little blue slider bar going across when it reaches the end here. That should be calculation complete. It also gives you a little counter here saying how much of the percentage is done, 12% done, and so on. Let's wait a little bit here until this thing is finished. Okay, we're almost done now. 97, 98, 99, and 100% done. It gives us a little box here saying analysis complete. We click on that, say OK, and it'll open up something called a plot window. Okay, so what is this plot window? Well, we have about 37 different directional sample variograms here because we incremented the azimuth by 30 degrees around the clock. And for each one of those horizontal directions, we also had dip at 30, 60, and finally at 90. So Sage is going through all of those variograms. So let's add a little bit of information here. We go up here and say show pairs. Okay, so now we have the pairs for each of these sample variogram points. We could say auto off. So that means it's stopped, and we're just looking at one variogram. Here's our title, shear gold, And remember I said the largest variogram would be 200 meters, so that's what we see, the lag distance on the x-axis, gamma h on the y-axis, and over here we have our azimuth and dip. So this particular variogram, sample variogram, is calculated at an azimuth of 225 degrees, dipping minus 50. We can look at the next one. So we see 255 at minus 50. We can click through all of these. I'm looking at, there's our vertical one. So azimuth of 45 at minus 90. Actually, if you're going straight down, the azimuth is irrelevant, right? All azimuths at minus 90 would be the same variogram. So this is it here. Okay, very short range by the look of it, right? Okay, so let's go look at the next one, which is more interesting. This is one where the azimuth is 45, so that means it is parallel to the shear, the strike of our shear zone, right? And the dip here is 0. So this is one that we're very interested in. And if we look at that, we see, oh, wow, that's got a really long range here. Because here's the sill. We're using the parallelogram, so the sill is 1. So that's going across here. So you can see that by the time this thing gets to the sill, we're going to have much longer than 200 meters. That's a very long range. Now, if we go perpendicular to that, which would be another 90 degrees, so we go 75, 105, 135, so 45 and 90 is 135. So this is perpendicular to the strike. And sure enough, if we look at, here's the sill at 1, we come across here, so that would have a range of probably a little bit less than 40 meters, right? So we have a very, very strong anisotropy here, which is what we expected. Okay, we can close this, and I want to show you a couple of other files that Sage has provided from calculating the variograms. So I'll exit this, and exit this, exit. Okay, so that's closed. So Sage provided us with these various files. Here's the .sag file that it created, remember? You want to have a look at that and see what it looks like? It's actually a text file. There's nothing really secretive about it. Let's see if I can open it. Yeah, there we go. We opened it. So this is what an SAG file looks like. So there's a title across the sign here, the number of variables or columns, if you want. I think 1, 2, 3, 4, 5, 6, 7, 9 is a number of columns in this file. Here's the header record here, and these ones and zeros tell Sage whether it's a continuous variable or a categorical. So notice 0, rock type, categorical, all the rest are continuous. And then the data. So that's a .pli file. You can create those things yourself if you have an editor and you'd rather do it outside, but it's easiest to do with Sage. Okay, well, the first thing we might want to look at is the report file. This is a good file here, so we're going to open that as well. Here we go. So this is the report file, S37, a three-dimensional variogram program. It gives us a project title, shear, gold, gives us a date and time that it started. Here are the input files and the output files. Then something about the data selection. So we see the max and mins for the coordinates. We see the acceptable geology codes, shear. And then it gives us the directions in which to compute sample variograms along with the angular tolerance, the dip, the lag, and the lag tolerance. So like I said, there are about 37 of them here. So we have a sample variogram for each one of these azimuths and dips. Okay, then it gives us a summary of some of the options we chose. Do not make the log transform, do not use local anisotropies, do not make down the whole variogram. It says we're using the parallelogram, gives us a summary on the bandwidth, tells us how many records it read and how many it selected. So the difference between these two would be 48,155 in the shear zone, and the remainder would be in the host domain. Okay, summary statistics then. The maximum is 3.87 grams per ton because we set it that way. Here's the mean, the variance, and the standard deviation. We usually like to look at the mean and remember that, 0.57, and the variance, which is, no, the standard deviation, which is 0.69. So 0.57, 0.69. Why do we want to remember those? Because those are important when we start looking at lag statistics. Then we have a summary for each one of the 37 directional sample variograms. So here we have the sample variogram for azimuth 45, dip 0. We have lag 1, 2, 3, all the way down to lag 50. It should be the number of pairs, the average distance for that leg. Drift, ignore that. Here's the G correlation. That would be the correlogram value, or 1 minus the correlogram, if you will. And then we have some lag statistics. So this tells us the average of all of the samples that were found at the head of the separation vector. And this is all average of all of the samples that were found at the tail of the separation vector. And then the same thing for the standard deviation at the head and tail. So if our pairing of data is representative of the sample data set, then these values here should be pretty close to the global. So the mean head should be equal to the mean tail, and that should be pretty close to 0.57, which is the mean of all samples. Likewise with a standard deviation, 0.71, 0.70 should be pretty close, so lag standard and lag tail deviation should be pretty close to the standard deviation of all samples. So we look at these and we can see that sometimes this is not true, 0.4545. So in another video, I will go over in more detail how we can look at lag statistics critically and decide whether or not, well, they will tell us why the sample variogram appears the way it does and whether it's legitimate and whether we should consider trashing it or keeping it. What's wrong with it or what's good about it? We can learn a lot from lag statistics. And then you see we have the same thing for all 37 of them. Okay. So that's a pretty thorough report, and it finally ends up saying program ran to successful completion on the date and time. So that about wraps it up. Variography with Sage 2001 Part 2. We now have 37 directional sample variograms. They are in this file au.pli. And if I look at those, I can show you what that looks like. That is the file that we are going to read with Sage to make our variogram models. So again, you see title, azimuth and dip, and it'll have azimuth and dip for all, and the data for all 37 directional sample variograms. What Sage will do is take these sample variograms and model them all at once, simultaneously. So, all right, we'll do that in Variography with Sage 2001 Part 3, the next video. Stay tuned. Thank you.